Thank you very much. So yeah, moving from resource depletion towards regenerative building materials. So how do we do that? So what we currently have is within the construction industry and us as designers and architects, we deal with single-use materials, produce single-use buildings, but we want to move to infinite reuse, which we're still not there. So building with earth is the most or the greenest solution we have got. That's very important to kind of keep in mind. What we have is what I call the FES group of materials. We've got fibers, natural fibers like straw, hemp, sawdust. We've got earth, obviously from which we can make light earth blocks, etc. We've got stone, structural stone, stone foundations, and timber. And those four categories form basically everything we should be working with and dealing with. I mean, everything else is just kind of prolonging the problem and delaying basically tackling the issues. We've got a problem. Amongst many problems, we've got a modern problem. So if we've got a curtain wall building, the U values for the glazed part of the building, which may be 20, 30, 40 meters, would be 1.3. And if this was a masonry, it needs to be 0.18. So that's very strange. Both of them pass building control. But if one of them is a COB building, traditional COB building, 600 millimeter thick walls, it will have U value of 0.55. And the curtain wallings, we're still going to have 1.3. And there we are. We've got a COB building, which is 60% better thermal insulation, cannot pass building control. So yes, we and this is basically one of the main issues. We've got materials, but actually we, in a way, in an effective way, we're not really allowed to use them the way we can. But let's go further back. And how did we get here? So the oldest can surviving houses are built of stone because in the 12th and 13th century, construction in timber was incompatible with durability. So we've got 15th century, we've got yeoman's house. In the Middle Ages, Kent's largest yeoman's house could easily take 70 to 80 large hardwood trunks, at least 100 years old, for the main frame, and another 250 for the smaller trees, up to 20 years for the joists and studs and rafters. But then in Kent, after 17th century, building in timber declined because of all the trees that had consumed by the furnaces of the iron industry and by insatiable needs of shipbuilding. And then later on in 17th and 18th century, we've got obviously revival of building with brickwork, which obviously with the Industrial Revolution, this kind of reaches its peak in terms of complexity and technicalities. And then later on, mid-19th century, the arrival of Portland cement. And this slide I particularly find interesting, how you've got these kind of brick slips that they were basically encasing in Portland cement. So that's kind of still kind of holding on. And then later on, early 20th century, the big earthquake followed by a huge fire in San Francisco, and then one building left there, which happened to be reinforced concrete and seems to have persuaded majority of people to move in that direction. So it's the before and after. So before concrete, we had the majority of the time for larger buildings, load-bearing masonry, timber floors, and obviously after that, everything was basically infilled with cement and sand and gravel. So you've got all these huge voids that basically need to be pumped up, where water, limestone, sand and gravel are lost forever. So we've got a more than 100 years later, the concrete tap is still running. So at the turn of the last century, modern concrete was thought to be as permanent as the stone it mimicked. None of that turned out to be true. Modern concrete fails and fractures in dozens of ways. Heat, cold, chemicals, salts, and moisture all attack this seamlessly solid artificial stone, weakening it from within and shattering it from within. And there is this misconception between Roman concrete and that something that stood for hundreds and thousands of years and modern concrete, but they're not the same materials and they don't have the same chemical bond, they don't have the same ingredients, and they behave completely differently, basically, with weathering, etc. Apart from that, we've got not only global warming, but we're also running out of sand. In a typical year, the world uses enough concrete to build 27-meter high, 27-meter wide wall ring around the globe. But even when you look at the industry, the mining industries and gravel kind of sand industries guidance, this is an extract from the MPA document, you can just see that even they are spelling out the fact that we've got a big issue. And they're talking about increase from 253 million tonnage in 21 to 323 million tons by 35, a level not seen since the 1980s. Turning to supply, it is clear that whilst recycled and secondary aggregates are providing a valuable source of supply, even larger tonnage of primary extraction will be needed to meet overall demands. With historic long-term replenishment rates for primary aggregates well below 100%, future long-term supply pressure are building up. There is particularly the case of land-won sand gravel supply, the contribution of which to total aggregates supply is likely to continue to decline over the next few years, replaced by a combination of marine sands, gravel, and crushed rocks. So obviously, I mean, yeah, marine sands has huge environmental impact, and it's extremely carbon intensive, and yeah, it's obviously something that we shouldn't be doing. But in a way, they're spelling it out. We've got an issue. We don't know how to solve it, but we've got an issue. But how about cement? So this is just a photograph of one of the kind of Kettons cement works, which produces a tenth of the UK cement. And then where does their limestone come from for the cement? So that's the location of the quarry, and then you can see that's also the factory there for the cement is there. But when you look at closer, it's a huge quarry. It's empty and there's no mining equipment. So that was really kind of strange to see. And when you look at further, zoom out, and you see these white dots, really small dots, all the way scattered around. And when you zoom in on them, you find lots of mini mines scattered around. And then you wonder, so why are they doing this? And you go to the geology viewer, and then just you see that actually the limestone at the quarry around the factory is 4 meters thick, which basically means that they've used it all up, and it's empty. So clay instead of cement. So again, so that's the two things. One, clay being the active binder, which is combined with various fibers to produce various whether it's light earth, plasters, etc., which allows this kind of circularity and infinite reuse. And then the other is cement as the glue, where basically afterwards resource can be only downgraded. And then I'm going to take you through a few projects that I've kind of done over the years. This is something that I did back in 2015 when I was living in Devon, in rural Devon. We formed the Community Land Trust, and I did a design for affordable eco self-build, which was for passive house. And I had the kind of privilege to meet Barry Honeysett, and he was the engineer on it. And through his kind of knowledge and the material, we developed a design for, I mean, very straightforward COP building, a 450 COP and straw bale on the inside with some kind of timber cladding. But then the whole point here was that it got me going of like using the material from the side, using the straw from fields nearby, and kind of not using concrete, etc., etc. So that was the kind of my first insight into that world. This is Barry's section of his design with concrete-free foundations. And then again, we had things of like we plant 10,000 oak trees to offset the carbon of the construction, wild meadows, green ponds with cleaning the grey water and improving the biodiversity outside, etc., etc. And this was this kind of a visual of those houses. So this didn't go anywhere. We didn't get anywhere with the Dartmoor National Park. And after a couple of years, I came back to London. And then I started to wonder, is earth construction scalable? So I managed to get in touch with some good engineers from Expedition Engineering. And then we took part in a competition for a new university building in Sofia. And then again, we had a look at the site reports for the soil reports, and it was good for rammed earth. So the design was for 30-meter high rammed earth walls, and this is in seismically active Bulgaria. Yeah, so expedition engineering did all the calcs for that. So it was 40 centimeters thick wall with insulation on the inside, but then of course it's a self-supporting facade rather than load-bearing. So behind that you had a timber superstructure to carry the floors for. And so one interesting thing is that we also went for earth screed below the floor tiles instead of cement screed on top of the COT. And then when the engineer did some calcs, he also said that that potentially could really help with seismic activities and kind of counterbalance. Following that, did another competition with expedition engineering, and this one was also with Atelier 10. And we, in this case, actually I started thinking of, you have to design the material system before even you start designing the building. So you needed to first find out what you're working with, what you can do with it, how you can use it, and then you see what kind of spaces this would lead to, which is something very uncomfortable for an architect because we don't tend to think in this way. So here the selection was, again, soil from the site, hemp panels, structural hemp panels for the walls, and then you had timber frame as well with ripped COT panels spanning across. And here also, again, we went for earth screed, and then we also had these earth panels lining the soffit as well. So it almost like I tried to think of a way of stuffing as much earth as I can within the building. So this is visual. Again, the external is all based on Martin Rauch's kind of his way of building larger panels and lifting them and placing them on the side, because it's a kind of it's a convincing way to put in a presentation, especially for somebody who is not familiar with this type of construction. So yeah, Atelier 10 did the carbon calculation, and then they came up with the figure. And when we put that figure into a chart, I should have said that actually we also had the concrete pre-foundations here. We did rock piles, vibro rock piles. But yeah, when they did the chart, and this was a kind of to me it was a kind of quite shocking that after all that, going for as local as possible, majority kind of natural building materials, lots of fibers, timber, etc., lots of earth, you're still kind of just between B and A. And then you're thinking like, I mean, what does one need to do in order to be A+ or A++? It's bonkers. So moving on then to the Tribeca. So this is a job which has already been built. It's in central London, next to King's Cross, for large developer. We had typical kind of concrete frame building, but here I managed to move the conversation with the client and the contractor early on with the help of Roland Kibo to perhaps start to use the soil from the site for the internal walls of the basement. This is where we had blockwork specified. And with the help of Roland, I went to site. I asked the builder to give us some fresh samples as the pile rig was kind of pulling out of the soil. I dropped them off at Roland's place, and then he went to H.G. Matthews to the factory, played up with them, and then made this block and gave it to us. And then by that time the client still didn't know anything about it. Then we took that to the client, presented it, told them that's their material and it comes from the site and and they loved it. I mean, they were cautious, but then they really loved the idea. So we kind of continued pushing. Then Roland and H.G. Matthews did more blocks and did various tests, and at the end we managed to do it. We managed to do all the internal perimeter walls, so not the dividing, but the perimeter walls. We did them with earth blocks from the site. We had to do 3 different mixes, and unfortunately the structural engineer selected the strongest mix, which had a lot of added sand. But nevertheless, the important thing is that it happened, and the mortar also came from the site with added sand. And this is one of the big rooms, which will be now a lab space, a laboratory. And the earth blocks here are almost 6 meters high. They're obviously tied back to the concrete wall, but yeah, it's self-supporting. The engineer had a nightmare, but we managed to get there. We were also lucky that the block layers were from Moldova, and apparently a lot of their grandparents' homes were constructed with earth blocks, so they were very familiar with that, which was a big surprise and very lucky. Photographs of close-up of cleaning them. So yeah, so following on from that, so the site next door is the same client. So we managed to, although we are now not the architects on next door, we designed the planning, but they selected a different delivery architect. We managed to convince the client plus the architects and engineers and the contractor to do the same next door. So in a way, in this instance, the site is the quarry again. Much more than it was on the first phase. And then, yeah, a lot of the soil is already at H.G. Matthews now, and we're basically having various tests done for justifying doing the internal dividing wall. So this is test H.G. did for the fire test for the earth walls. And it passed to our fire resistance. So again, for the next phase of the development, internal walls with fire rating up to 2 hours, those blocks can be used there. So other blocks that Roland is playing up with at the factory is light straw blocks, and this is something that again we've got a strong interest. We want to find different products and different solutions that we can then implement in business. I now, over the last year, have been attending the factory once a week, where we had meetings, we test various things and discuss how things can progress forward. And it's been extremely kind of fulfilling, and a lot of kind of very insightful information and ideas have come through. So this is basically the straw clay block fire test that Jim and Roland did at the factory. So you can see basically it's so Roland has been playing up with different mixes to make a mix which does not catch fire. I mean, as you can see from the video, it basically chars on the other side, but nothing really happens to it. And this is not even that thick panel. I'm not sure how thick was it, but I don't know, it was 50, 60 mil, something like this. So yeah, nothing happens. I think at the end, I think Jim's hand gets too hot from the torch and from the reflected heat from the clay block, so he just has to let it go. But as you can see, nothing will happen to the moment you take the flame away, it all just kind of self-extinguish. So afterwards, we sent this video to somebody who is a fire engineer, highly knowledgeable fire engineer, and he said, based on the video with the blowtorch, there is a large chance that the straw clay block classify as A or B, but you cannot really tell without proper tests. But I mean, yeah, it's still, we have a very different perception of those materials, and we think, oh, there's natural fiber, oh, it's gonna catch fire, etc., etc. But actually, if you go through rigorous tests, if you adjust the mixes, actually we can come up with products that can basically, yeah, do the right thing and can be scaled in larger buildings or just kind of large scale applications. So we are also looking through, so that's on the left is Roland's kind of clay straw light block, which is really good for infill between studs because it's quite sturdy. It's got kind of solidity to it. And also we're looking into insulation block, and we're playing with various different fibers, and in this case also, so it's straw and sawdust. Quick one, we're looking for H.G. Matthews, we're looking potentially extending a pub for them, and the brief is to basically do a vote using their blocks. So again, here, the design process was very different. I mean, rather than kind of starting and looking at plans and ideas of shapes, etc., it was, what is the material, how can you use this material, what is the kind of the vote technique that needs to be used in order to be able to create the shape, etc., etc. And this was like, with Roland, we spent quite a few hours just kind of discussing that and going through the various different voting techniques. And it's this kind of insightful knowledge through people who understand the material and people that will work with the material is crucial for us as architects to be able to actually design with these new materials. We can't do this by ourselves. So we really need kind of the industry, the earth building industry's kind of input and knowledge in order for this to happen. So again, so this was one of the sketches that we did early on about how the vault will be, the curve of the vault, how it will be shaped, what kind of blocks, because again, we need to work with the standard blocks, how they can be cut and how many, etc., etc. So yeah, and again, in here, the brief would be, blocks, and then straw clay insulation, then a locally sourced timber, which would be split using cladding, cleaving planks, and then concrete-free foundations with shingles. So yeah, we've got resource storage versus resource depletion. So this is the kind of in a way the two ways, the two options we have. So what we're currently looking is structural stone with timber for the structural stone for the columns, timber for the floors. So in a way that will give us base, and this is I'm talking for more like larger buildings, base where internal dividing walls, internal partitions, light earth, earth blocks, earth screeds, and earth panels for the soffit. So then it's, and then clay plasters, etc., etc. So that's kind of that, just an illustration of what that would kind of look like. So we have to remember that earth deposits are everywhere. So we need to utilize them as much as we can within our building. So in a way, that's going to be should be our first material to go to. Unlike structural stone, which basically is sparse. So this is like a map of the geological map of the stone. So you can see here, there's the kind of chalk and limestone seam as it goes in. And these are some of the main quarries where you can extract structural stone and the kind of relative close proximity to the UK. And I just want to focus on the Portland one because this is one of the main ones, and obviously is the Isle of Portland. And when you go there, when you go actually zoom into the map, you only have the Isle of Portland, then little bit here, everything else, a little bit here, everything else is actually chalk. So that really good limestone, which we can use for structural use and et cetera, we don't have that much of it. And actually most of the quarries there are on the ground. So again, it's very sparse when you look at from that bigger map. Actually, there is not that much there that can be used. And when you look at go into the section of that, you can just see it's only below the top layer. Then there is the Charity series. This is basically the kind of the limestone that we can extract. Everything else is anything but. It's not good for structural use. So again, in terms of depletion, it's limited. What we've got is limited, and we really have to use it in the best possible way. So there we are. So we have to move away from the single use resources, and then go towards moving towards infinite kind of reuse, where you have these multiple cycles of reuse. And this is a kind of little illustrations, the last slide, and it just kind of hopefully will make people think about, I mean, the different scale of buildings, of course, and what we can do. But actually, the kind of the small and the medium scale is where earth must be pushed as hard as possible, I mean, even structurally as well. And then you've got probably the medium to kind of a bit larger one, where it's a bit of a hybrid of earth, stone, and timber, perhaps for the top bit. But then that's it. At some point, is then buildings become way too high, way too wasteful to even bother doing anything about it. So yeah, thank you very much.